Okay, let's start. Last time we started to discuss stability, which is a subject which is at least of same importance as accuracy for at least for a time-dependent discretization scheme, but in general, as we have seen already, that these things are very strongly connected. And we are now on the way from the semi-discrete formulation to a fully discrete formulation, have already formulated the one-step theta method with its most important example, explicit Euler, theta equals to 0, implicit Euler, theta equals to 1, and Crank-Nicolson, theta equals to 1/2. And we looked at the stability of these methods. Now, we will do this a little bit more precise today. Let's compare, let's repeat what we did. Maybe before I start, there will be the old German transparencies. There will be a few new English transparencies. In particular, this chapter, as you might have seen, the English version is considerably extended compared to the German version, and there is one discrepancy in the notation which I mentioned already last time, but I hope it's not too bad. So the time step, the discretization parameter in time in the German edition is denoted by k, and in the English edition it's denoted by tau. So you will have a mixture. It will change from German to English transparencies and vice versa. I think all the other notations should be the same. So one way to look at this, we started from another direction, but one way to look at this is to say, actually we have to look at a system, a linear system of equations. It is basically, again, written down here. It comes either from the finite element or from the finite difference method. And what we consider are one-step methods as indicated. That is, we compute the approximate solution at the new time level, only knowing the approximate solution on the time level below. So we computed n plus 1 by knowing an approximation at the level n. And you see here the resolved difference quotient here in this formulation. So and we have seen already that behind the evaluation of this function phi, depending on time discretization, time level, and old approximation. In general, in the implicit method, there is a solution of a set of equations. You see this again. Here we have the exact formulas for the theta methods, and you see a part of the case theta equals to 0. We have here to evaluate an inverse matrix. That is, we have to resolve a set of equations by measurement perturbation, but of course also by rounding errors that we want to have. We want to have that this perturbation is not enlarged, is not enhanced. We have seen in the equations, in looking at the stability of the parabolic equations, often it's even better. We have something like parabolic smoothing. That is, we have that the initial data, and by this, of course, also differences of initial data, and by this, of course, also perturbances in the initial data, are damped exponentially. And the exponential term is determined by the lowest positive eigenvalue which we have, which, of course, assumes that all eigenvalues are positive, which assumes that we are in the situation where we at least have some Dirichlet boundary condition or something similar, but here we require less. And we will see what we have seen already, what kind of assumptions this brings with us. So that means the error level always stays below the is not higher than the error level at the initial instance of time, and the approach. Oops. Okay, this we can skip. So we have seen it, at least in a situation where it's a little bit of an old notation here. The matrix is denoted by Q. I think in the English version it has another name, but I forgot what the name of this matrix of the eigenvectors was. So now we assume that we are in the diagonalizable case. We are always in the diagonalizable case if the matrix is symmetric, of course. So if you have pure diffusive forces, there's no problem with that. And one can view now the situation we are looking at in this more abstract fashion as a situation which is not so far away from the pure diffusive case. Meaning that there's still we still have a basis of eigenvectors which forms this matrix Q. The eigenvalues forms the diagonal matrix lambda. That is, we can transform to the coordinates given by the eigenvectors, and that leads to the decoupling of the system. That is, in these new coordinates we now have m is the number of components which we have. We have m independent linear equations. And of course, how they behave is only now dependent on the eigenvalue, which is on this diagonal position. That is, for positive eigenvalues lambda I, we have strongly decrease. For 0, of course, we have a constant solution. And for negative, we would have an exploding component. So in some sense, it is basically the same saying, I'm only looking at the diagonalizable case, or to say I'm looking at the one-dimensional model problem. Because the one-dimensional model problem, that is this scalar ODE with a factor lambda here, is, here it's a little bit more neutrally denoted, is representative as long as we can diagonalize. And therefore it makes sense to formulate the conditions at this level and saying we consider a method A stable if it is applied to this model equation is such that the solution, the discrete solution, is non-expansive for all parameters lambda, which then later on, of course, are played by the eigenvalues, as long as the real value of this lambda is bigger than 0. So if we look at the corresponding solution components, why only the real value? Why we're only looking at the real value? If we look at the corresponding solution component in the ODE or in the ODE system, we have the complex. If we would have a complex eigenvalue, we would have the complex exponential function, which again, say e to the lambda plus I being the imaginary unit, mu, and this is then multiplied with t or with minus t, and then we have the real part, which has this explosive or diminishing behavior, and we have an oscillating part. So the only thing what complexity in the eigenvalues bring is that the solutions start to oscillate. But it does not influence their growth or diminishing. Therefore, only here the reals. The real part, sorry. Okay, so, and we have worked this out, and we have seen what comes out. The only thing we have to look at is this is, so to speak, our corresponding acceleration factor, which comes in, and on the continuous level and on the discrete level with our theta method, our acceleration factor is this quotient, this evaluation of this specific rational function here called capital R at the argument minus lambda times k, minus lambda times tau. So this function r now takes the place of the function basically ez, or e minus z, ez. So this is a rational approximation. What we have done, we have substituted the exponential function by a rational approximation. And okay, to substitute the exponential function by a rational approximation, let's assume this is the exponential function. The most simple rational approximation, of course, would be this one here. This is 1 plus x. Where do I find this here again? For which theta, obviously? Theta to 0. Is that correct? Then I have 1 plus z over 1 here. That is, this is the explicit Euler method here. And the others then are real rational functions. Then we really have something here. The Crank-Nicolson and the implicit Euler method then. So it depends, so to speak, what this now stability function does with negative arguments here. So the argument which goes in is minus the eigenvalue times the time step. What it does with arguments with negative real part. So this gives us the requirement that, first of all, it shows us that A stability is equivalent of requiring that the function is in modulus less or equal to 1 for arguments with negative real part. And it makes sense that we define the domain of stability where this is fulfilled. And then A stability means that the negative half of the complex plane has to belong to the domain of stability. And if we look at our methods, and you will hopefully work this out in the exercises, we see for theta equal to 0 we don't have A stability because this is only the unit disk which belongs to the stability domain. For theta 1/2 we have exactly the left-hand side of the complex plane, and for theta equals to 1 we even have more, which is on the one hand side not forbidden, but it also shows that there is damping. There is an acceleration factor less than 1 for components which actually should not be damped if we apply this method. So there are also problems with the implicit Euler method in the sense that it might happen that it's too good. In the sense it is too smoothing. Okay, so this we have seen, how this relates, the stability with the positioning of the A stability of the position of the stability domain. And now, okay, so now if we look for A stability, then the explicit Euler method is out. And we have to distinguish somehow between the implicit Euler method and the Crank-Nicolson method. And in principle also everything which is in between theta 1/2 and 1. Later on we will see, or in principle we know this already, as the Crank-Nicolson method is related to viewing this difference quotient as a central difference quotient, but the implicit Euler method views this difference quotient which we apply in time as a backward difference method. We know already that the consistency error on the one hand side is of order 2 for Crank-Nicolson, and for implicit Euler only of order 1, so to speak, as bad as in the explicit method. So from this accuracy point of view, which we go more in details later on, one would say, okay, it's clear one should take Crank-Nicolson. It's the same effort, but it brings more precision in time. But there are other aspects to consider, namely in conjunction with stability. And in terms of A stability, the methods are the same, but there's another notion of stability, namely the notion of L stability. Yeah, here we see again, of course, that this is not an astable method, because if we are interested in this half of the behavior of the approximation, we go down. It's okay. Here we're still between 0 and 1. This part is okay. This part is also okay, but then, of course, we are leaving the corresponding domain of stability. And that can only be saved, and we discussed this already last time, if one says, okay, it's not really necessary that the stability function has this behavior modulus less or equal to 1 for all possible arguments. It only has to have this property for our specific minus lambda I times tau. But the lambda i's are given. So the only way I can, so to speak, require that I stay here in this area and do not go out by making my tau small in relation to the lambdas, by requiring that the tau equals k is smaller than 2 over the minimal eigenvalue. The maximal eigenvalue. But the maximal eigenvalue again is growing in h as h to the minus 2. And this then leads, as we have seen last time, it does not mean that the explicit Euler method is total rubbish, but it means if we apply it, if we want to take the advantage of non-solving a set of equations, then we have to obey the stability requirement saying that tau over h square, and that's what we got out. It was 1 over 4, I think, in 2 dimensions for looking at the 5-point stencil. But in any case, we always have a requirement that tau over h square is bounded. So if we refine the h by a factor 1.5, we have to refine the tau by the factor 4, by a factor 1 over 4, to keep this relation. So therefore, one usually says for parabolic problems, things are a little bit different. If convective forces get more and more prominent and we come into the range of hyperbolic problems, of wave equations, of pure transport equations. But if this is not the case, one usually still prefers the implicit methods. And now we have to distinguish somewhat between the implicit Euler and the where is the function again? Here it is, between the implicit Euler. So this is how here is theta equals to 0. Now what kind of functions we have? We have the case theta equals to 1. So this is just 1 over 1 minus z. So somewhere I have to draw now 1 over 1 minus x, I've called it here. So what is this? What does this function do? It is stays where it should, so it starts at 1. If I go in this direction, I have this part going to infinity, so I get 0 as a limit, so it's nice, and I go here. And this already looks much more than an approximation of the exponential function, that this straight line here far in this direction. And that is also a good behavior, what I have here. What does that mean? It means the more I go in this direction, that is, let's now think of a given tau, of a given time step size. If the bigger my eigenvalue is, that is, the more oscillating my eigenfunction is. This is, of course, now refers to our specific knowledge, which we, for example, we have for the 5-point stencil. We have seen how the eigenfunctions, the eigenvectors look like. the more it gets damped. The more critical this component is in the sense that it brings in we're not going to say discontinuity, but a little bit of roughness in the solution, the more it gets damped. So this is the case theta equals to 1, and that behaves very nice in this case. So what is the third case which we have? It's 1 plus 1/2 over 1 minus 1/2 of x. So, and what is now here the limit value for x going to minus infinity? This is analysis 0, I would say. Minus infinity. Okay, what is the limit value for x? What do I have to take here as a value? You have to tell me, otherwise I don't go on. -1, yes. So I get here this value, and I get a behavior somewhere it crosses, I think at 2. This is bad drawing, very bad drawing, but what the important thing is, what kind of behavior do I have now for the high frequent components? There's no damping, it's just the other way around. The higher frequent the component gets, the less it gets damped here. And that can cause problems. And therefore we have an additional notion of stability, that is the so-called L stability. Where is it? And we call method L stable if the stability function has the property that the limit is 0 if the real part converges to minus infinity, which is the case for the implicit Euler method, and it's not the case for Crank-Nicholson and the other versions for theta. Okay, so what we have seen up to now, only the implicit Euler method is L stable. There's a little bit of if you have done a little bit of difference method for ODEs, I would hope that you have dealt also with stiff equation. Who has heard this notion of stiff equations, steife Systeme? Nobody? Never heard this notion of a stiff system? But you have looked at ODEs? I would say there is no example from applications which is not stiff, but anyway. So what we have here is a stiff system in the sense that we have usually we have enormous range in the eigenvalues, and therefore in the behavior of the solution components. If I have two solution components with eigenvalues, say lambda I and lambda 1 and lambda 2, which are far, far away, this is one and these are all the others, then how would my solution behave? Let's start with only look at the one-dimensional situation, which is accordance to our diagonalization procedure. The lambda I, the solution would behave like this. A reasonable solution. That would be, so to speak, our solution components for those guys here. But what about this thing here? The solution, of course, is the model problem. The model problem meaning, as we had it, y prime plus lambda y equals 0 or equals something. Okay, now we have the solution component for I equals to 1. And what I have to draw here now? What kind of picture I have to draw for this very small positive eigenvalue? Sorry. Do I do it correctly, or maybe I just have to look at the other way around? Sorry, it must be the other way around. Here and here, and this is then large. This is what I mean. So what do I have to draw here? How does the solution component now look for a very large lambda I, lambda 1, for this equation here? Yeah, but extremely damped. It will basically jump down to 0 more or less immediately. That means there is one component where you have to resolve very, very small here. This is the stability. And here you don't have. And that is what a stiff system causes of problems. And we have here typically, we are led here to, of course, typically time discretization of PDEs lead to stiff systems, and maybe also systems which are independent of this background. So, and if you look at the corresponding monographs of, this monograph, I would say, should at least have been mentioned if one dares to speak about difference methods for ODEs, for initial value problems. There is a 2-volume, or maybe meanwhile 3-volume monograph by Heira et al. Heira, Nurse, et Wanner. And the first volume is called Non-Stiff Problems. And the second volume is called Stiff Problems. So to deal with stiff problems, and that is the whole point why one then says, okay, we need something like linear multi-step methods. But you know what linear multi-step methods are. Have you heard of linear multi-step methods? PDF methods or something like that. That is the whole background of linear multi-step methods. Okay, and of course, with the notions of stability, there's a little bit of a weaker notion of stability. It's the so-called strong A stability, which at least, but the Crank-Nicholson method is also not a strong A stable. In the strong A stable case, one would not require the 0 limit, but a limit less than 1. And in the Crank-Nicholson, we have seen it's the limit 1. Okay. Now, let's try to write this down a little bit more. What are the consequences now in terms of solution evolution, in terms of stability for the full equation? And we can phrase this here a little bit more abstractly, as we have seen already. So what is the situation? We have a spatial discretization, whatever we would like to have, finite differences, finite elements, whatsoever. This leads us to a discretization matrix, and we still have the assumption of the basis of eigenvectors. The eigenvectors are here denoted by Wi, and the eigenvalue still by lambda I. So the one-step theta method, as we have seen, can then be written as, if you want, as a linear stationary method for right-hand side 0, in the sense that there's a matrix, and in each step there's just multiplication with this matrix. If we are in the situation there's only initial data and the boundary data are 0. So, and this EH this matrix EH tau, this just reflects what we have to do. It has inverse of the matrix, which defines the set of equations we have to resolve. And it has then multiplied with the matrix, which is the modifications of the right-hand sides we have to do. And maybe we can go back and see this matrix again. Probably, I'm not sure whether it's somewhere here. No, it's not here. Okay. Okay, here it is. Here, this is the matrix. This comes from the set of equations we have to resolve. That is, have to modify the right-hand side. And you see that is where our stability function stems from. So our stability function is just, or this matrix is just the stability function evaluated at minus tau times the matrix. And here we see again on the continuous level in time, we would not have this rational function. We would have them eat the exponential with the negative argument. So this is the approximation stability properties which come from this relation, which play a role. And in addition, we have seen if we then add if we add a right-hand side, QH, then on the continuous level, we would have this term in the solution representation. That is what is called the variation of constants formula, or sometimes it's also called Duhamel's principle. And you see, I haven't mentioned this, but you see what happens. You see how we come to this solution. What do? We consider, so to speak, for each instance of time, the right-hand side as an initial data. And we start the solution at this instance of time S, as if this would be the initial data. Then we get this part. And we sort of overlay all these solutions by forming these integrals. And this overlaying process, of course, at the discrete level becomes much more clearer, because here we just only have to sum up. So this integral becomes a corresponding sum on the time discrete level. And to these representations, we now come back. Okay, so this is this operator EH n specific EH n tau, EH tau specifically, and EH tau n is just the nth power of it. So this gives us the representation of the solution, as I said, for purely having initial data. And so to speak, what we have seen in this specific case, we now make a general theory out of that and say, okay, let's have a one-step method which has this solution representation here. We have seen examples for that. And this R should be the corresponding stability functions, such that this relation holds true now for the eigenvalues. And then we have the following equivalency of statements. So the assertion is the following three statements are equivalent. The first is the one-step method is non-expansive for the model problem and all possible eigenvalues. The second one, it's non-expansive with respect, so this refers, so to speak, to the scalar case. We plug in the eigenvalues and we just look at the scalar ordinary differential equations. The second version refers to the system. And then we need a matrix norm. And the assertion is, if the matrix norm is chosen such that it's the matrix norm induced by the discrete scalar products with which, and now our second condition comes in, and we would like to have that according to this scalar product, our eigenvectors are orthogonal. So this, at this level, this, so to speak, determines our spatial norm which we use. So that means either L2 norm or discrete L2 norm, but it can also mean, in the case of a symmetric A, of a symmetric bilinear form, then we have seen in this case these eigenvectors are not only orthogonal with respect to the discrete L2 scalar product, but they are also orthogonal with respect to the A scalar product. So in this case, we do not, here in general, so to speak, we say something here then that is the assertion about the discrete L2 norm, and there are specific cases where we even say something about the corresponding energy norm. So to speak, the real norm from the finite element problem. So that is the second assertion. And the third assertion just is we have to have that this operator, or this matrix here, is just a norm, and the norm is now the norm induced by the matrix norm induced by the vector norm less or equal to 1. So that is, so to speak, the compact version of stability here. And later on we will see, then in the next step we will see what are the consequences of that, and in the step after we will see how we can we relax a little bit this requirement to get weaker forms of stability. So, okay. Let's have a look at the proof. The proof is quite simple. It only takes advantage again only of this orthogonal. Was soll ich damit jetzt? Of this orthogonal basis of eigenvectors. Okay, where we are. Da war schon, ja. Okay, so. Okay, here we can see again the assertions, but we have them, we see again the assertions, and we prove in the direction 1, from 1 we conclude 3, from 3, 2, and from 3, 1. So, okay, let's start. So, the first assertion, we start from the assertion that the one-step method is non-expansive. But here we have seen that this is equivalent, so meaning we're dealing with a model problem, we're dealing with scalar equations, there's only a number to deal with. And the number which decides whether the solution is growing or not is this number, r of minus lambda I in modulus. So this is just the characterization of the stability for the eigenvalues. Now we want to transfer the scalar equation to the scalar formulation to the system formulation. So we represent the initial data in terms of this eigenvector basis, and then we can of course do always, and as it is an orthogonal basis or orthonormal basis, we even know how the coefficients are. They're just the Fourier coefficients. And now we compute what does the operator, what does the matrix do with this general, now, so to speak, we can view it as initial data, but it's just a general vector here. So, okay, so the operator goes through this sum here. And here on the level of the eigenvalues, we have seen that this only means that also for this modified matrix here, this Wi is an eigenvector, and the corresponding eigenvalue is now just given by this expression here. So again, we have a linear combination formed with the eigenvectors, and we have the corresponding norm in the induced norm, and then we know that there is an identity between this norm squared and the corresponding norm of the so to speak, Euclidean norm of the vector. So we take all the coefficients which we have here. We have to square this. We have to square this and have to sum up. And here it is not assumed that the Wi are normal, are normed, and therefore also this norm appears here. You can also compute this identity directly. You form this scalar product of this sum and the sum. You multiply everything out, and everywhere where an index I comes together with an index j, I independent of j, this term has to go away by orthogonality. And the only thing what remains is this part here. And the same thing is this identity here. That's exactly the same argument. So if we now compare, so what has happened is this factor here has come in addition into the sum. But this factor is less or equal to 1, so we can estimate this part here by this part. And so we have now estimated, oops, where are we? We have estimated the norm matrix applied to some vector squared by the norm of the vector squared. Now we can, of course, cancel the square, and then we see this is nothing but the statement that the induced norm is less or equal to 1. Because 1 is a stability factor, is 1 times norm of u, 0, and the induced norm is the best stability factor. But you can also compute it by the formula supremum over whatsoever. So that is what the one thing. Now from 3 to 2. This is obvious. Why is this obvious? From 3 to 2. Yeah, this is just this argument. If I have a matrix or have an operator with this property, then I have non-expansiveness, because this just means I always have, this is, so to speak, my best factor in the stability, and the best factor is at most 1. And now back again to these were already the complicated parts, or what you mean, if you might call it complicated. And now again back to the scalar case from 2 to 3. So we have to deal, we want to say something about this factor, but if we now take specifically, we take specifically in the operator the eigenvector, that means this term pops out. This is just this here. This can be estimated by this here. That is the stability assumption. Now we cancel here the norms of the eigenvector, and then we have what we would like to see, namely r at minus lambda I tau is less or equal to 1. That was the assertion. This is a misprint here. That is not 2 to 3. That is 2 to 1 here. Okay, so now we have different ways to note stability, and in general we can say very briefly a method in this sense is stable. A one-step method is stable if the solution representation only for the initial data fulfills this requirement. The matrix norm is less or equal to 1 in the norm induced by the vector norm, which stems from the scalar product, the underlying scalar product. But of course, the assumptions are strong. The assumptions are really orthonormal eigenvector basis. This is very, very close to saying the matrix is symmetric. In the symmetric case, we know that we have all these things. There are some other kinds of matrices where we have this too. Not sure whether they play a role here. You might know that the characterizations for having an orthonormal eigenvector basis is that the matrix is normal. There are more normal matrices than only the symmetric ones, but I think in this range so maybe it's a little bit of cheating what I'm doing here. You can, if you don't like this cheating, you just say we are talking about symmetric matrices. So, okay. Now let's assume that the method is stable. and let's see what kind of stability result we get for the solution. So in which way we can now estimate the solution in space and time dependent on the initial data and then the right-hand side. In a similar way as we've seen this, of course, also for the continuous problem and for the semi-discretized problem. And what we get out here is the following. So if we it's this estimate, so we can estimate for each instance n. So this is an estimate which is pointwise in time. It's not a we can estimate the solution at every time level n in the corresponding norm. That's always here the same norm, the induced norm, by the norm of the initial data, and this tau times sum of the right-hand side data. And here you might recognize that this is again something like a time integral from 0 to Tn with a quadrature rule approximated. So this is very similar to the estimates which we had here, but one term is missing. Which term is missing compared to the, or what kind of term you would maybe expect if you remember how the estimates looked like in the case of the continuous problem or in the semi-continuous, in the semi-discretized problem. What kind of a factor is missing here and here? Exactly. The damping factor, the exponential damping factor is missing here. So in this sense, it's really only a weak result. It says the error in this sense is not exploding, but it doesn't say anything about damping. And at this level, it's also not otherwise possible, but then for that we have to look here for our assumptions. Namely, the assumptions are that the eigenvalues are greater or equal to 0. That is, we allow here for the 0 eigenvalue. We allow for the constant component in the solution. We allow for the pure Neumann case. The other situation was positive eigenvalues, V-elliptic problem. And we will then have to see later on which kind of improvements we can do if we don't have this assumption but really require that all the eigenvalues are positive. Okay, the proof is relatively simple. We just take the solution representation, put the norm on top of it, and that's it. So the solution representation had this term here, EH tau to the power n times U0. If we put the norm on this, we can get the norms through because they are all compatible norms. We have an induced norm, and because we are dealing here with an induced matrix norm, it's also submultiplicative, so we can get the power out of the norm. All this is possible, and so we end up with this term here. And now, concerning this term, we see already the above result. Namely, we know that this factor is less or equal to 1. So we see already this part of the estimate. Now with the right-hand side, it's similarly simple. We can also put the norm by the triangle inequality through the sum, through the powers, and all these parts here. And again, this term does not do us any harm. This is less or equal to 1. It doesn't gain us anything at the moment, but it also does not do us any harm. And the only thing which is left, which is, so to speak, different from the continuous situation, is this factor we have seen already. But this factor also does not do us too much, because the only thing to deal with this part, we have to know what this matrix does with the eigenvectors. And also for this modified matrix, this omega I is an eigenvector. What is the eigenvalue? If I only look at the matrix here in brackets without the inversion, the lambda I changes to 1 plus theta times tau times lambda I. And now inverting the matrix is meaning going to 1 over. So this is this value here. And this value is again here under our assumptions on the sign. We need already a little bit less, but under our sign assumptions for the lambda I, and this also allows for lambda I equals to 0, this is less or equal to 1, this factor. So in the end, the norm of this operator, that's always the same argument, is less or equal to 1. So this doesn't change. This we can forget, this we can forget, and then only this sum here remains. Okay. So how could we relax these requirements? Let's assume that we have method, and that is of importance then for discretizations of convection diffusion equations where the convection becomes dominant. Let's assume we have a relaxed estimate. We don't have less or equal to 1, but we have less or equal to 1 plus k tau. So that means this factor is allowed to grow in time, but it's only allowed to grow in time according to the time step size here. This, of course, this estimate goes over directly to the corresponding estimate for the stability function here. It's basically the same arguments as we have applied them. Now what does that mean? Now we don't have just the factor 1, but we have the factor 1 plus k tau. And we have seen it is this factor which, say, for example, for the initial data appears then in the nth power. So we have to look at the nth power of this thing. And in general, if tau and n would not have to do anything with each other, of course that would be helpless. Then, of course, this factor would explode if n would become large. But now these things are related in the sense that tau is the step size in time, that is, tau is just capital T over n. Or to put it otherwise, if the n becomes large, the tau becomes small. Because dealing on the fixed time level up to capital T. And that means that what we have here is nothing but the sequence which you might have started with in introducing the exponential function as the sequence, as the limit of the sequence 1 plus x over n and the whole thing to the power n. This we see here again, and we only have to know that the exponential function is to be estimated by that. So the n can be written then as n times tau over tau, and then we get this estimate here. So that means as long as we are in a fixed time interval, and as long as this factor k is not too bad, it might be possible to live with this constant here. It's a big constant, but okay. But of course, if we are interested in having something for large time intervals, it's clear that the estimate becomes weaker and weaker by the increase, by the exponential increase of this factor, that the result becomes quite doubtful. Okay. Now, how can we do better? And let's we'll only look at this at the case for tau equals to 1, that is for the implicit Euler method. And now we would like really see a little bit of damping. So now it becomes of importance that and you see here a little bit of a problem. The minimal eigenvalue. Okay, we can do this also for the Crank-Nicholson, but here it's only written up for the implicit Euler method to make it simple. So we have seen if we estimate this norm here by 1, of course we don't see any damping. So what we have to do is we have to estimate this norm, or what is the same thing, we have to estimate the R value, corresponding R value, by something which is less than 1. And here we can do that. It turns out that we have here to look at the minimal eigenvalue. To check this, we have to go again into this representation of vectors by the eigenvectors representing the norms, basically what we have done, and then we have sums, and the dominating thing is then here the minimal eigenvalue. Of course, this has to do with the structure of the function that we have here, 1 over 1 plus lambda tau. So that is, we have to deal with this factor. So actually what we can get in is we can get in this factor here. This is a diminishing factor. It's not only 1 in the estimates, it's really a diminishing factor which becomes smaller and smaller in time. And if we want to have it look like the exponential decay, we can also do so if we restrict ourselves to time step sizes smaller some upper level. This is quite reasonable because at least the length of the interval is a natural upper bound for the time step size. And usually one can take this tau 0 much, much smaller. And in this case, we can even estimate this, a function like this, by a corresponding exponential function. The factor lambda is then that's not so good as we are used to have it. It's not the lambda min anymore. It's something which is a little bit smaller than the lambda min. Otherwise, it would not work. Because we have, of course, maybe you think this is strange, because what I would like to do is, I'm here on the negative part. I have the exponential function, and I have the, this would, so to speak, the 1 over r1 plus x function. Of course, this 1 plus x function is not above the exponential function. So what I have to do is I have to tilt this a little bit, that I stay above the exponential function in the range where I'm interested. It only works on a fixed range, but this fixed range comes from the tau 0. Maybe you try to work that out. So in the end, if we make the lambda a little bit smaller than the lambda min, then we can even estimate a term like that by an exponential term. So in this sense, we get our exponential damping back into the estimate. Okay, maybe we skip this example. It's not so interesting. Okay. Okay, let's change topics a little. Not change topics, but adding another aspect. So, of course, what is now missing is the order of convergence estimates. Now we have to put everything together. We have now the stability. We have the order of convergence for the semi-discrete situation. We have the stability of the time discretization. Now the hope is that this all can be put together in an estimate. And this we will do then on Friday, I would say, on an estimate which is in space and time in corresponding norms, and which has an spatial order term, our hk, depending on the method we are using, and a time order term. And we have already some idea how this time order term could look like. Usually it will be tau, it will be of first order in time, and in the Crank-Nicholson case it will be of second order in time. Okay, this we will do, but before doing so, we will remind ourselves that there's still another approach to stability if we change the norms, which of course then also in some sense change the norms in the outcoming order of convergence results. And when we started with the finite difference method, we did not have all this variational material. So the only thing we could do is we could look at matrix properties, and we came up seeing that certain matrix properties leads to L infinity stability. And the L infinity stability there was then together with the consistency estimates, which we did there with brute force, led to our first order of convergence result for the 5-point stencil, for example. Now, later on, we have seen that also in the finite for the finite element methods, we may have L-infinity stability, we may have a maximum principle, but it requires certain properties of the underlying triangulation. That was this situation with the sum of the corresponding opposite angles must be below pi. Or a weakened version of that, every angle must be acute, must be less than pi half. So there are situations where we know there is a maximum principle for the spatial discretization. Therefore, it's quite a natural question. Now we have a specific class of temporal discretization. Now it's quite a natural question to ask, under which condition do these fully discrete schemes inherit the maximum principal properties? Do we have to have further assumptions? Or might it even be that we can relax a few of the assumptions that we had before? And there is maybe a little bit of a hope in this direction, because if you think, in the stationary case, we were not so easily able to deal with the pure Neumann problem. The pure Neumann problem has not a unique solution. It needs a compatibility of the data, which is quite natural, and then the solution is a one-dimensional space. It's only determined up to a constant, because we only have derivatives. The equation cannot see constants. On the other hand, if you now look at the time-dependent problem, also with pure Neumann data, and you remember what we did in conjunction with the solution representation, with the classical Fourier analysis, we were able, in these very specific cases of one dimension or two-dimensional space on a rectangle, to write down a unique solution for the, say, heat equation with pure Neumann data. Because what do we have to do? We have to look at the corresponding spatial eigenvalue problems. We have to be able to say something about the eigenvalues and about the eigenvectors. And we, at least in these two cases I mentioned, we could do this very explicitly. One can do this much more generally, but then not explicitly. And the only difference was that now there was also the eigenvalue lambda equals to 0 with a corresponding constant eigenfunction. Meaning that in the solution representations there's a component which is not damped to 0. The limit for t to infinity in this case is not 0, but as we have seen, what comes out, it's just a constant, and the constant is the average mass. It's the integral over the initial data over in one dimension over the length of the interval and correspondingly in 2. That means in this situation we have at least a unique solution, so we might hope that we can also have a maximum principle there. That means we might not need the assumptions we had in the maximum principle business, which basically said there has to be a little bit of Dirichlet boundary conditions. So let's go back. It's now a long time ago, but I hope you reminded a little bit. It is this famous formula 132 in the English version and I think 128 in the German version. Okay. Here we are. So let's see again what the conditions were. So, okay, this was just purely algebraic structural conditions on the discretization matrix. The first set, the diagonal entries had to be positive. then the off-diagonal entries had to be non-negative. Then we would like to have that the sum is non-negative, and at least for one index there is a strict inequality, it's greater to 0. And if you remember what that means, if we think again of the 5-point stencil. In the 5-point stencil, at a point which is far away from the boundary, we have our entry 4, and we have all our 4 minus 1s. So we have the 0 here. And only exactly in the situation where, so to speak, 1 or 2, or maybe in extreme case also 3 of those neighboring points belong to Dirichlet data and therefore are not here in the equations anymore, then the sum becomes positive. So this is the second part, is a sort of a requirement of at least a little bit of Dirichlet data. Let's skip about the fourth at the moment. This A hat matrix was the matrix which dealt with the eliminated Dirichlet data, and they had the same sign conditions and the same sum conditions. So the A tilde matrix was this rectangular matrix composed out of AH and A hat. There is this condition which says that the Dirichlet boundary condition, so this is the part which reflects the Dirichlet boundary conditions. There's this condition which says any Dirichlet boundary condition should influence, so to speak, the solution in some way. It should not be just a 0 in the corresponding, what is it? In the corresponding column of the matrix. That's all not so critical. And now here comes the critical assumption, AA. That was this guy here, saying that the matrix is irreducible. And we said already that we said it's critical. It was not so clear at that point why it is critical, because in our discretizations of the elliptic case, it was fulfilled. And we discussed already a relaxation of this condition, namely, where is it? It is this condition, what is called here 4 star. Which, what means irreducibility? It means that it has different equivalent meanings, and one is we can go in the sense in the corresponding adjacency graph. That means along connections where the corresponding entries in the matrix is not 0, we can go from every index to every index, which again means everything depends on everything. It's not possible to reformulate by reordering the matrices, the equations and the unknowns, the system in a block, in a block, say upper triangular fashion, that we can first compute a part of it, and with this knowing the part of the solution, we can compute the rest. This, of course, is quite nice to split a problem like this, but irreducibility means that it's not possible. And therefore, here we relax the requirements in the sense that we only want to go from some index, which is here denoted by R1, to another index, but we only want to go from an index where the sum is 0. That means in this interpretation from a point far away from the boundary, we would like to go to a point which has this sum property, and which in this interpretation means we want to go to a point close to the boundary. That is the relaxation, and we have seen together with this requirement for the full rectangular matrix that the sums are 0, then we could still have corresponding maximum principles, strong. We had various versions. We had the weak maximum principle, strong maximum principle, comparison principle. This was impossible. And now there's a problem. Why is there a problem? Why? Now we will formalize it in a second, but maybe we can first do it like that. think now of the things what we are doing, namely doing this step-by-step method, and write everything in a big matrix, and you have a big vector. So the vector not only contains the unknown for one time level, but for all time levels. And now think of this matrix. That is, so to speak, our discrete problem we have to look at. And the strategy must be now for this matrix which comes out, which we have to make more clear what it is, to identify all these properties, which I have now listed again. Why is this matrix not irreducible? Why can this matrix not be irreducible? When we write it down, it will be clear that it's not irreducible. But why it's not irreducible? Why do we have a system where everything belongs on everything? On which the unknowns or the components of the solutions at the fifth time level, at which do they depend? Let's say we have 10 time levels. We look at the fifth time level. On which components do the components of the fifth time level depend? Or let me ask you another way. Do they depend on the sixth time level? No. It would be pretty bad if the future would determine the present. Fortunately, this is not the case. So this matrix cannot be irreducible. So we have to deal with this weaker version here. Okay, so let's start. Maybe we'll not finish it today, but let's start in writing down the properties. And to summarize that, it's here a little bit ordered. There are different collections or sub-collections of these properties, and here this is, so to speak, reminded what we can conclude from them. So the numbering is the same as we had before. So the first version was, or it was not in the way we have derived. It was not the first, but in some sense the basic thing is the inverse monotonicity of the matrix, which just means the matrix is invertible and the inverse matrix has non-negative entries. And what we have seen is what we need for that were the requirements 1, 2, the first half of, these were the sign conditions, the first half of 3, that was the sign conditions at the sum, and this relaxed irreducibility condition. If we add in addition, so this has nothing to do with data at the moment. If we want to have a comparison principle, which is here denoted by CP, meaning if we have initial data, we have data in the problem, right-hand side data, and Dirichlet data. Let's use this notation for this underlying stationary problem, and they are ordered, then the solutions are also ordered. Then we have in addition that the matrix part, which deals with these Dirichlet data, has to be the right sign condition, that is this property 5. So if in addition we have this condition 6 star, which was that the sum over the full matrix, including the Dirichlet data, is 0, then we have a weak form of the maximum principle. There's some alternative. And finally, we have also a strong maximum principle if, in addition, we have done now the properties, and now we really need the irreducibility and this condition 6. So the program now is write down this very, very big matrix in the right-hand side and investigate under which assumptions these conditions, which we now reminded, are fulfilled. So, okay, we start. So this is the long vector. So we have our time discretizations. This produces us the solution at the first time level, the second, and finally the nth time level. So we now have, these are, so to speak, our non-eliminated degrees of freedom we would like to compute, and correspondingly this M1 bar is now the new M1, if we pick up this notation and think a little bit in terms of the finite difference method, but it does not only apply to the finite difference method. So now we would like to write down the set of equations. So we need to have the matrix CH, and we need to have the right-hand side PH. And the matrix CH, this is my assertion, looks like that. It's a lower triangular, block triangular matrix in the sense that the first time level does not depend on any other time level. It depends on the zeroth time level, but that is part of the data. The second time level only depends on the first time level, and so on. And here we see again, of course, this matrix is reducible because it's already in this reduced form. And here the matrices we have are just the matrices which come from our theta method. So these are the matrix we have to invert, and this is the matrix with the corresponding sign which is multiplied with the old time level. Now we have the right-hand side. The right-hand side consists of the corresponding evaluation of the right-hand side we have after the discretization in the semi-discrete version, which produces us the QH, which belongs, of course, which consists of the F parts, of the distributed parts, but in the finite element case it could also include the boundary integrals, which come from inhomogeneous flux conditions or inhomogeneous mixed conditions. This is all in the Q, multiplied it by tau, because we have multiplied it through. And at the first time level, we still have the part coming from the initial data here. So the data, now we have to fix the data, which have been the Dirichlet data, so to speak. And now let's go this further step. Wait a second. Now we have to specify further the Q. And the Q, as I said, it depends on the F, which now corresponds to those terms which I just have mentioned. Right, distributed right-hand side, but possibly also those boundary integral parts. And it has this part from the eliminated Dirichlet data. And now if we remind that theta method means that we look at everything as being an approximation at this possibly intermediate time level, Tn minus 1 plus theta times tau. And that values which we cannot evaluate at this time level, we have to look at the corresponding convex combinations. That's the way we have put up the method. Then it's reasonable to say with the Dirichlet boundary data it's exactly the same, because it stems from this part with the corresponding elimination of the known values, which are moved to the right-hand side of the equations. So that is the assumption that the QH has this specific form. So, and here again, not only the matrix AH, but also this matrix AH hat appears, and the point is now from the properties of AH and AH hat to conclude the corresponding properties of the matrix CH. And now we need also a matrix CH hat, which deals with our, so to speak, our Dirichlet data. And our Dirichlet data are all the Dirichlet data from all the time levels. But, and that is, so to speak, the one which saves us in the situation with the pure Neumann data. So all this might not be here, these things, because we will allow also for the pure Neumann case. We have, so to speak, in all the time we have something like Dirichlet data, and that is where it comes from. It's the initial data. The initial, if you think of the problem is on the time-space cylinder. And the boundary values are at the bottom, the initial data, and at the mantle of the cylinder. So even if at the mantle we don't have any Dirichlet data, any values prescribed, of course at the bottom we have values prescribed. And that is, if you want, the reason why we can allow for, in this time-dependent case, we can allow for the pure Neumann case. So this is now our vector of given data, so to speak, our Dirichlet data. Has also a corresponding dimension, which we can compute. And now we have to write this right-hand side in terms of minus a matrix CH hat, so the notation is absolutely analogous, times this vector plus the vector E, and this is the matrix. In this matrix, so the vector E is just tau times F at the corresponding time levels. And the matrix CH, so to speak, in the usual situation, it only contains this different AH hat parts with the corresponding factors in front of that for the corresponding data old and new, but initially, not so sure, is that correct? Is this correct with the dots? It's maybe not quite correctly depicted. So this should, of course, so these dots here connect this part with this part. And these dots here connect this part with this part. And in addition, initially, of course, we also have here the factor which deals with the initial data here. So the initial data, if you go back, the initial data are part of our given data, but of course they act only at the first time level. Okay, so and now let's see what we can do about the properties. And there's one assumption which comes up quite naturally, that we need this assumption. At least I do not know how to do without this assumption. And this assumption. So we would like to have that the diagonal element of our spatial discretization matrix multiplied by tau and theta bar is less or equal to 1. What does that mean? In the case, what does this mean for the implicit Euler method? What does this mean for the implicit Euler method? Yeah, the light is, it doesn't mean anything. It's no requirement. It says 0 less than 1 should be correct. And in the other cases, it's a step size requirement. It's a step size requirement which looks very similar to the step size requirements we have seen for the explicit Euler method for stability. Because if we think again, what is AH? Think again of the 5-point stencil. What is the diagonal value element? It's 4 over h squared. So it's again it's basically the same requirement we had before. It's a requirement at the quotient tau over h squared. But it comes here from a totally different background. But the good thing to note is, if we do the implicit Euler method, which I said already, I think 95% of all simulations are done with the implicit Euler method, then there's no requirement. Okay, we will see how we will need this assumption. So let's go through a little bit through the properties. The first thing is we would like to have that the diagonal elements are positive, and we see that at the diagonal, where is the matrix? At the diagonal, we have 1 plus tau theta times the diagonal element of A. So this is satisfied if the diagonal element of A is positive. We could even allow for a little bit of a negative diagonal element of A, because we still have this 1 here in the sum. The next thing is we would like to have, this was the condition 1. The condition 2 is that the off-diagonal elements are all non-positive. So we look at these blocks here, and you see if we are off the diagonal, the 1 is gone here. The sign of the entry is just determined by the sign of the A matrix, because there's only a positive factor in front of that. So if we have the property 2 for the A matrix, this is the same thing here for these blocks. For these blocks here, it's again the same thing. We are off the diagonal. But here we also have diagonal entries. And here in the diagonal entries we have -1 plus tau theta bar A jj. And you see the requirement we put were just that this quantity is even less than 0. For that specific point, it would be sufficient less or equal to 0, which is maybe not so a big deal whether I require that something is less than 1 or less or equal to 1. But anyway, but here we need it. We need it just for the corresponding correct sign. So these were the sign properties. Now we have this thing with the summation, and this is a thing we can still discuss today, and then we will continue on Friday. The summation, so this part we have, this part we have. So now we have to look at the summation. So we pick a row in this big matrix and we just sum all the entries of this matrix. And we would like to have that it's positive, that it's not negative, and we would like to have at least one of the sums, which are here abbreviated by CR, are positive. And we have seen this is a sort of a Dirichlet requirement here, as we discussed it. Now, if we take the same notation for the underlying matrix A and introduce correspondingly AJs, then we can try to compute these CRs. Let's start with the first block. So the indices R are the indices of the first block. This is meant here and here, and that means that okay. What does that mean? Maybe we go back to the matrix. I only have here one projector, unfortunately. Oops. Yeah. We are here, and here we only have this matrix. So we sum over here. So we get a 1 from here. We get tau times theta times the corresponding A sum. And now you see, if the corresponding A sum, it only needs to be greater or equal to 0 to ensure that we have here something positive. That's again that the initial data act as Dirichlet data. They bring in the positive values here which we need. What is with all the others? With all the others we have this part and we have this part. So the 1 is cancelled by the -1 here. And the factors in front of the corresponding sums are tau, and the other factor is theta plus theta bar. Theta bar is 1 minus theta, so theta plus theta bar is 1. So it just means what is left is tau times the A sum. So the sign is this quantity preserves the sign of the A sum, but it does not get positive. If the A sum is 0, then it's 0. So in summary, we have here satisfied these sum conditions, and we have automatically by the Dirichlet boundary, by the initial conditions, satisfied this, let's say, Dirichlet condition. Okay, and then we continue next week on Friday.